Welcome back to High School Physics Explained, and today I'm doing part 3 on my series on the workings of MRI. And if you've watched my previous 2 videos, here's a quick recap. We talked about how nuclei have a thing called net spin that causes them to have a slight magnetic dipole. We're going to concentrate, of course, on our hydrogen nuclei because they are the most abundant atom in our bodies. When you place those spinning nuclei in a magnetic field, a strong magnetic field, of course they align, and they align in a strong magnetic field in such a way that they are either parallel or anti-parallel. Now, most of them align in a parallel direction, and only a few align in an anti-parallel direction, and the proportion of those aligning parallel and anti-parallel is determined by the strength of the magnetic field. These anti-parallel and parallel are also precessing around that magnetic field. And so here I have 4 representative poles of the spinning nuclei, and as you can see that they're precessing, and of course as a net result you have a net magnetic field up. Now, of course, the antiparallels are doing the same thing as well. They also produce a net magnetic field as so, but for all intents and purposes, the 2 arrows combine. So really what we end up having, what they refer to as the magnetization vector, that is running perpendicular. So that's where we're up to. Now, the question then is what happens next? But before I do that, I want to briefly talk about the rate at which these atoms are precessing. And this refers to a concept of the Larmor frequency. And the Larmor frequency is the frequency that this atom or this magnetization vector is precessing about an axis. And it's determined really only by one variable, and that is actually the magnetic field that these atoms are aligned in. All other variables are constant. The first is this, which is called the gyromagnetic ratio, and it is a unique value for every particular atom that has a net spin. And in terms of hydrogen, that value ends up being 26.7 by 10 to the power of 7. So that's unique to hydrogen. And of course 2 imply a constant. So if you were to place a hydrogen atom in a magnetic field strength of 1 Tesla, you can then calculate the Larmor frequency, that is the frequency at which this precesses. And so to do that, you just need to know the gyromagnetic ratio, and that was 26.7 by 10 to the power of 7. You multiply it by the magnetic field strength, which in our case is going to be 1. We can have it, of course, a little bit higher, and we divide that by 2 pi. And that gives us a total of 4.27 by 10 to the power of 7 hertz. Or, more frequently placed, it is basically equal to 42.7 megahertz. Now that is very significant because that frequency of 42.7 megahertz happens to be in the same range that we would classify radio frequencies. And that becomes the subject of my continuing lesson. So here I have my precessing atoms, or I select a few. I've got, of course, some in the antiparallel section, but of course the combined effect, of course, is that the magnetization vector is in the upward direction, aligned with the external magnetic field. So what happens now is this. I now get a radio frequency coil and I fire a radio wave that happens to have exactly the same value of the precession frequency over here, or the Larmor frequency over here, of 42.7 megahertz. Now what happens here is a concept of resonance. And resonance is simply a property where if you fire or provide a forced frequency onto something who has the same natural frequency, then this substance or thing, whichever you're firing at, will actually absorb the energy that is actually received. And there are lots of natural everyday examples you might see of resonance. So for example, you're pushing a person on a swing. That swing has a natural frequency. If you push at the exact same rate, then you're going to find that the swinging is going to increase quite dramatically. That's resonance. The same is, for example, if you have a nice wine glass and it produces a lovely note, let's say 250 hertz, and when you click the edge of the glass, if you fire a sound at the same frequency, 250 hertz, then what is going to happen is the glass is going to absorb that energy, and it is very possible that it will shatter that glass because the energy will continue to be absorbed. The glass will continue to vibrate at a greater intensity, and of course eventually the glass won't be able to cope with that and it will shatter. It has nothing to do with loudness, it has everything to do with resonance. So in terms of MRI, by firing a radio frequency that is equivalent to the Larmor frequency here, you actually get resonance. And then two things are going to happen, and we're going to discuss those in detail. So here you have my four representative nuclei spinning that are definitely out of phase. I'm only dealing with these four at the moment. Now, when a radio frequency is fired, they start to now, of course, precess in phase altogether. And that's the first thing that happens. When the radio frequency is fired, for resonance to occur, the first thing that happens is you're going to starting to get precession going in phase. Now, what is the significance of that? If you combine all your arrows together, you can see that the magnetization vector for just this upper section of the parallel section of the precessing atoms is now leaning towards the right, or in fact, it's not leaning towards the right. Of course, this magnetization vector is also rotating, but because it's in phase, we now have a wobbling magnetization vector. It's no longer vertical. And remember, its reason it was vertical was because all of them were out of phase at one stage, and the average was that it would actually give you a vertical magnetization vector. Now that they're in phase, we're going to see this vector rotate around this axis. But of course, the same is true for the anti-parallel section. So we have a magnetization vector going this way for the parallel ones, and then we have a small value of the anti-parallel ones over here. So here we of course have the magnetization vector for the parallel atoms, and over here we have the magnetization vector for the anti-parallel atoms, and now they're of course in phase. What you end up getting is a net total. So initially, before you had resonance, you had a magnetization vector that was actually vertical. What you now get, of course, is the sum total of those two vectors. And you can see that now we have a net vector that is now leaning towards the right. Now, of course, again, this vector is actually not stationary. It is actually rotating about the axis because, of course, these atoms are actually precessing. But the net result from a sort of rotating frame of reference is that it's leaned over. But the second thing that happens is that the number of parallel and anti-parallel numbers change. What we have in resonance is an increase in the number of anti-parallel. And in fact, the total number of anti-parallel to go into the higher energy state will be equal to the number of anti-parallel. And so what you end up having now is an equal number of parallel and anti-parallel. And of course, both of those will give you a net magnetization vector. So here is my magnetization vector sum total for the parallel ones over here. My anti-parallel ones, of course, has a net magnetization vector, but because of the fact that we have no more anti-parallel, we now have a larger magnetization vector for the vertical over here. What does that mean? Well, of course, what that means is what we end up having is my magnetization vector sum total now goes into a vector that is completely gone horizontal. This vector plus this vector is equal to that vector over here. And so what we say is that the magnetization vector, which was once vertical, has been knocked down. And the maximum angle that it can be knocked down by is actually 90 degrees. Of course, the rate at which this happens is determined by the strength, the frequency that's applied, and the time that it's applied. So the processing going to go in phase takes some time, and of course so does the fact that the number of antiparallels going from parallel to antiparallel also increases, and so this would get knocked down at a particular rate. As a result, the maximum may be 90 degrees, but it actually may be less depending on how long the radio frequency pulse is on. The summary. So number one, when you get resonance, number one, you start to get precessing in phase. Number two, what you're going to get is what we call a spin flip. And that spin flip is from parallel going to anti-parallel. And of course, the net result is that your magnetization vector, let's say called the M magnetization vector, gets knocked down to a max of 90 degrees. And that in essence is what the resonance situation is. So there you have it. There's part 3. The next step is to understand what happens when the radio frequency gets turned off, and what we end up getting is a process called relaxation, and that is actually what is measured by the computers to produce an image. So that will be part 4. Thanks for watching. Bye for now. I hope you found that video useful, and remember, like, share and subscribe. Oh, and if you have a comment or a question, or you'd like a concept for me to explain to you, please drop a comment down below. I'm Paul from High School Physics Explained. Bye for now.